A braking resistor, also known as a dynamic braking resistor, serves to dissipate electrical energy generated by a motor during braking or deceleration. When a motor is braked or decelerated, it continues to generate an electromotive force or EMF due to its momentum. This EMF can cause a voltage spike or backfeed that can damage sensitive electronic components such as motor drives or other equipment connected to the motor control center. The braking resistor provides a safe path for this energy to be discharged, preventing voltage spikes and protecting the equipment. It converts the electrical energy into heat, which is then dissipated into the air. The braking resistor is typically applied to motors that require controlled or rapid deceleration, such as elevators and cranes, conveyor systems, fans and pumps, and CNC machines. It may not be necessary for all motors in a motor control center, depending on their specific application and braking requirements. However, it is common to have a braking resistor for motors that require accurate control over deceleration or that experience frequent braking. A braking resistor typically consists of multiple sections, each with a wire wound around a ceramic core. These sections are wired in series to increase the overall resistance and power dissipation capacity. The resistor is usually housed in an enclosure on the exterior of the motor control center to provide ventilation and prevent overheating. The function of a braking resistor is crucial in applications where motors need to decelerate quickly or stop precisely. Without a braking resistor, the energy generated during braking could cause several problems. Firstly, excessive voltage spikes could damage the motor drive and other connected equipment. Secondly, uncontrolled deceleration could lead to inaccurate positioning or even mechanical damage in applications like elevators or CNC machines. Thirdly, the energy generated during braking would have to be dissipated elsewhere in the system, potentially causing overheating or other issues. Braking resistors come in various sizes and configurations depending on the motor's horsepower and the braking requirements of the application. The resistor's ohmic value determines how quickly the motor decelerates. A lower resistance value results in faster deceleration, but it also generates more heat. The power rating of the resistor determines how much energy it can dissipate without overheating. When selecting a braking resistor, it is important to consider several factors. Firstly, the motor's horsepower and voltage rating must be taken into account. Secondly, the braking torque and duty cycle of the application need to be considered. Thirdly, the ambient temperature and ventilation conditions should be evaluated. The braking resistor must be sized appropriately to handle the energy generated during braking without exceeding its power rating. In some applications, forced air cooling may be necessary to dissipate the heat generated by the resistor. There are several types of braking resistors available. Firstly, wire wound resistors are the most common type. They are relatively inexpensive and can handle high power levels. Secondly, metal-clad resistors are more robust and can withstand higher temperatures. Thirdly, ceramic resistors are often used in high-voltage applications. The selection of the appropriate type of braking resistor depends on the specific requirements of the application. The installation of a braking resistor is relatively straightforward. The resistor is typically connected to the motor drive's DC bus terminals. It is important to follow the manufacturer's instructions and to use appropriate wiring and connectors. The resistor should be mounted in a well-ventilated location to prevent overheating. Proper maintenance of a braking resistor is essential to ensure its reliable operation. The resistor should be inspected regularly for signs of damage or overheating. The connections should be checked to ensure that they are tight and corrosion-free. If the resistor is exposed to moisture or contaminants, it should be cleaned periodically. The lifespan of a braking resistor depends on several factors, including the operating conditions and the quality of the resistor. In general, a well-maintained braking resistor can last for many years. However, if the resistor is subjected to excessive heat or voltage spikes, it may fail prematurely. When a braking resistor fails, it is important to replace it with a resistor of the same type and rating. Using an undersized resistor could result in damage to the motor drive or other equipment. Using an oversized resistor could result in slower deceleration. In addition to preventing voltage spikes and protecting equipment, braking resistors can also improve the energy efficiency of motor systems. By dissipating the energy generated during braking, braking resistors reduce the amount of energy that is regenerated back into the power grid. This can result in significant energy savings, especially in applications with frequent braking. Furthermore, braking resistors can improve the performance of motor systems by providing more precise control over deceleration. This can be especially important in applications where accurate positioning or speed control is required. The use of braking resistors is becoming increasingly common in modern motor control systems. As energy costs continue to rise and the demand for more precise motor control increases, braking resistors are becoming an essential component in many industrial applications. When troubleshooting motor control systems, it is important to check the braking resistor if there are issues with braking or deceleration. A faulty braking resistor can cause a variety of problems, including slow deceleration, inaccurate positioning, and voltage spikes. In some cases, a faulty braking resistor may even cause the motor drive to trip or shut down. There are several ways to test a braking resistor. Firstly, a multimeter can be used to measure the resistance of the resistor. A significant deviation from the rated resistance indicates that the resistor is faulty. Secondly, an insulation tester can be used to check the insulation resistance of the resistor. A low insulation resistance indicates that the resistor is damaged and needs to be replaced. Thirdly, a thermal camera can be used to check the temperature of the resistor during operation. Excessive heat indicates that the resistor is overloaded or faulty. Braking resistors are an important component in many motor control systems. They provide a safe and reliable way to dissipate the energy generated during braking, protecting equipment, improving energy efficiency, and enhancing motor performance. Understanding the purpose, function, application, and construction of braking resistors is essential for anyone working with motor control systems. Braking resistors are essential for safely and efficiently controlling the deceleration of motors in various industrial applications. Their ability to dissipate the energy generated during braking prevents damage to equipment, enhances energy efficiency, and improves motor performance. The correct selection, installation, and maintenance of braking resistors are crucial for ensuring their reliable operation and maximizing their benefits. Let's consider the specific components and design considerations in more detail. Firstly, the resistance element itself is critical. It's typically made from a high-resistance alloy, such as a nickel-chromium alloy, that can withstand high temperatures and repeated heating and cooling cycles. The wire or resisted element is often wound around a ceramic core, which provides electrical insulation and mechanical support. The ceramic material must also be able to withstand high temperatures without cracking or degrading. Secondly, the enclosure that houses the resistor plays a vital role in dissipating heat and protecting the resistor from the environment. The enclosure is usually made from metal such as aluminum or steel, and it often has ventilation openings to allow for airflow. The size and design of the enclosure depend on the power rating of the resistor and the ambient temperature. Thirdly, the connections between the resistor and the motor drive are crucial for ensuring a reliable electrical path. The connections must be able to carry the high currents generated during braking without overheating or causing voltage drops. The connections are typically made with heavy gauge wire and robust connectors. Fourthly, the thermal management of the resistor is a key design consideration. The resistor generates a significant amount of heat during braking, and this heat must be dissipated effectively to prevent the resistor from overheating and failing. Various cooling methods can be used, such as natural convection, forced air cooling, or liquid cooling. The choice of cooling method depends on the power rating of the resistor and the ambient temperature. The braking resistor's value in ohms is determined by the desired braking torque and deceleration rate. A lower resistance value provides faster braking but also generates more heat. The power rating of the resistor is determined by the amount of energy that needs to be dissipated during braking. The power rating must be sufficient to handle the energy without exceeding the resistor's temperature limits. The location where the braking resistor is installed is also an important consideration. The resistor should be mounted in a well-ventilated area where it will not be exposed to excessive heat, moisture, or contaminants. The resistor should also be located close to the motor drive to minimize wiring lengths and voltage drops. A control circuitry for the braking resistor is typically integrated into the motor drive. The drive monitors the motor speed and voltage and activates the braking resistor when the motor needs to decelerate. The control circuitry also provides protection against overcurrent and overvoltage conditions. Braking resistors are used in a wide variety of industrial applications. Firstly, elevators and cranes use braking resistors to provide smooth and controlled deceleration, ensuring the safety of passengers and cargo. Secondly, conveyor systems use braking resistors to stop quickly and accurately, preventing product damage and improving efficiency. Thirdly, fans and pumps use braking resistors to reduce the risk of water hammer or other hydraulic transients. Fourthly, CNC machines use braking resistors to achieve precise positioning and speed control. When selecting a braking resistor for a specific application, it is important to consider all of the factors mentioned above. A resistor must be sized appropriately, installed correctly, and maintained regularly to ensure its reliable operation and maximize its benefits. Understanding the principles behind braking resistor design and operation is essential for engineers and technicians working with motor control systems. Firstly, reviewing the motor specifications, including horsepower, voltage, and current ratings, is crucial. Secondly, the application requirements such as the desired braking torque, deceleration rate, and duty cycle must be carefully considered. Thirdly, analyzing the environmental conditions including ambient temperature, humidity, and potential exposure to contaminants is important. Based on these factors, the appropriate braking resistor can be selected. The resistance value and power rating must be sufficient to handle the energy generated during braking without exceeding the resistor's temperature limits. The enclosure should provide adequate protection against the environment and facilitate heat dissipation. The connections should be robust and reliable, minimizing voltage drops and ensuring a secure electrical path. The control circuitry should be properly integrated with the motor drive, providing accurate and responsive braking control. After installation, the braking resistor should be tested to verify its performance. The resistance value should be measured to ensure that it is within the specified tolerance. The temperature of the resistor should be monitored during braking to ensure that it does not exceed its temperature limits. The braking performance should be evaluated to ensure that it meets the application requirements. Regular maintenance is essential for ensuring the long-term reliability of the braking resistor. The resistor should be inspected periodically for signs of damage or overheating. The connections should be checked to ensure that they are tight and corrosion-free. The enclosure should be cleaned to remove any dust or debris that could impede heat dissipation. By following these guidelines, engineers and technicians can ensure that braking resistors are properly selected, installed, and maintained, providing safe, efficient, and reliable braking control for a wide variety of industrial applications.